You're at the mercy of Windows.
Yeah, no problem.
I'm sorry. Okay. So I'll talk today about little bit about biped robots and try and focus on optimization and learning. Okay. So what I'll do today is essentially try to talk about some basics of biped robots. Okay. What is gait? What is the basic dynamics? What is the basic control structure? And then I'll try and focus on optimization and then learning. Okay. So this workshop FDP that you're having is essentially to do with AI. Okay, and you would be in the last couple of days you would be hearing lectures on things like deep learning, other kind of learning procedures that are used in engineering. Okay. So today what I like to do is basically try and look at this specific application of biped robots, and then try and focus on why is optimization required, and second of all, where to use learning and where is learning required. Okay, and what kind of learning. Okay, so let's proceed. So biped robots basically come under this field of study called locomotion. And locomotion essentially means moving from one point to another. So you can move either on feet, like a biped, quadruped, or like a fish you can swim, or like a bird you can fly. So essentially locomotion covers all of this, basically moving from one point to another point. And if you look at robotics, essentially, then the early robots were mainly stationary arms. And why stationary arms? Because stationary arms are fixed, they don't need balancing, and you know the work volume. And this is the application in industries. Now, with the fixed arms, there was a requirement for increasing the work volume. So if you want to increase the work volume, then you have to mount the arm on a mobile robot, either wheeled robot or biped robot or quadruped robot, and then it can move around. So you increase the work volume. And the first attempts were made on wheeled robots rather than legs. Now, if you look at wheeled robots, most of these early robots, mobile robots, were wheeled. Now, why wheeled? Essentially because wheels do not need balancing, okay, and they are energy efficient. Okay, and that is the reason why most of these robots were wheeled robots in the early days. And not only in early days, even today, they are essentially wheeled for these two concepts of balancing and energy requirements. And wheeled robots can be holonomic or they can be non-holonomic. Now, what is holonomic and non-holonomic? Essentially, a non-holonomic system is one in which all the degrees of freedom are not independent. For example, in a car, in a normal car, the automobile that you're familiar with, you have one drive, the engine which is driving the wheels, and you have one steering. Okay, so there are only two inputs, the steering and the drive. But the degrees of freedom are three, x, y, and the theta, the bearing. Okay. So in a non-holonomic system, all degrees of freedom cannot be independently controlled. For example, this car cannot go sideways. It can go front with some steering angle only. So such systems are non-holonomic. Whereas holonomic systems are those in which all the degrees of freedom are independent. For example, vehicles which can go sideways or they can go at any angle. Okay, such systems are holonomic systems. For example, in a car, for example, let's look at this car, in which there are four wheels and the wheels have a special design. So on the wheel, each of these wheels, there are rollers, and the rollers have an angle to the main vertical axis. So if you look at the right side figure, the red line shows the direction of the forces or the velocities or the component of the velocities. So the component of the velocity will be normal to that roller. Okay, so which means that it is not in the forward direction, it has an angle. So by rotating the wheels in different directions, you can control the direction of this vehicle. So T1, T2, T3, T4 are the four vectors of velocity. And by making different combinations of this, we can move the vehicle in different directions, which means it can go sideways, it can go at any angle you want. So this is an example of a holonomic system. Okay. Now, this is the fundamental difference between holonomic, non-holonomic. Now, wheels are of different types, and for example, you can have track wheels, and we can have wheels which can combine between legs and wheels. For example, the left one is a wheel, the right one on the top is can behave like legs also, or like wheels. Then this is an example of the Athlete Rover, which is a cross between the legged system and a wheel system. Okay? So the wheels are used when it's going on flat ground. Why? Because it is more energy efficient. But the disadvantage of wheels is that it cannot go on unstructured terrain. For example, if there are obstacles, there are ditches, then the wheel can't go anymore. In that case, the legs start going. Okay, so it can step over an obstacle very easily. So this is a cross between a legged system and a wheel system. Okay, so this is called the Athlete Rover that was basically built for space exploration, and it is a hybrid kind of a vehicle. Now, interesting again is if you think a little bit, some things that are interesting to note is that all biological entities have legs, wings, or tails for locomotion. They do not have wheels. So robots have wheels. They are more energy efficient. They don't require balancing. But biology never prefers wheels. Okay, so we have legs, wings, or tails. No wheels. Now, so the advantage or the basic reason being that legs are more energy efficient, but are multifunctional. So you can sit down, you can stand, you can walk, you can lie down. With a wheel, you can't do all that. Okay. Now, recently there has been an interest in legged locomotion because the legs have some advantages. For example, they can walk over obstacles, they have less footprint, body can be maintained at the same height, they can perform different functions like climbing stairs, sitting down, etc., etc. Now, the third point there, body can be maintained at the same height. It's something that's very important. If you think a little bit, when we walk, also our horizontal, I mean the two eyes, have to be kept horizontal because that is our reference frame. So when we are walking also, those two eyes have to be always horizontal, and that can be done only with legged system. It can't be done with wheels. And that is one of the reasons why we have wheels. Sorry, we have legs. Now, the moment we come to legged system, okay, wheels and legs, we said there is a concept of balancing. So if you look at this video, this is the simplest one-legged walking system, okay, that has a spring, and it has an actuator. It has an actuator somewhere in the middle. Okay, so let's look at this again. So there is a spring, and there is a linear actuator piston cylinder kind just on top of the spring, and that's how it moves. So it can jump in one place, it can go forward, it can go backward, and it goes forward, backward, basically by changing the angle of the body, which is the red color horizontal board, which is the body of the system. Okay. Now, this is a very interesting video, which tells us two things. Number one, there are 2 degrees of freedom. One is passive, that's the spring. Now, on top of the spring, there is another degree of freedom, which is the piston cylinder there. So there is 2 degrees of freedom, both are linear. And there is one rotating kind of fellow there. So there are 2 degrees of freedom. One is the spring and the piston cylinder there, which is a linear actuation here. So that's 1 degree of freedom. The second one is the angle that the red kind of board makes with the horizontal. Okay, so you can see that angle is changing, right? And by changing that angle, it can jump in one place, it can go left, it can go right. Okay, so this is the the earliest example. Now, from study of dynamics, this is a dynamic system. What it means is that it is not static, it is not statically balanced. So if you want it to stand in one place, it cannot, it will immediately fall. Okay, so as long as it is jumping around and balancing itself by changing the top angle, it is balanced. But the moment it tries to stand in one place, it will fall down. Okay, this is the fundamental concept of balance in legged locomotion, that the legged system has to be balanced, it has to be dynamically balanced. Okay. Now, there are a lot of such devices which have been made in computer animation and devices, for example, a jumping kangaroo, four-legged walker, and others. Now, control of this device is taking place, or we enforce it by what we call the finite state machine. Now, what is this finite state machine? When we go back a little bit, we see that the states of this system keep changing. Once it is in contact with the ground, then it is not in contact with the ground. Again, the leg is compressed, then it's not compressed. Okay, it's compressed, or the spring is in the other direction, it's in tension. Okay, so essentially there is a finite state in between which this system starts moving, and that is what we call by a finite state machine. Okay, and this finite state machine has different stages. For example, if you look at this block diagram, on the top, when it's in flight stage, there is no contact with the ground. Okay, in the loading stage, as we come on the right side clockwise, on the loading stage, the leg spring is compressed. It has made contact with the ground, and the leg is compressed. So that's the loading stage. Now, in the thrust stage, what happens? The spring pushes the object upward. So that is the thrust stage, and then that is the unloading stage, and then there is the flight stage again. So if you look at this one-legged hopping robot, it moves from flight, loading, compression, thrust to uploading, and keeps doing this cycle. And each of these cycles are different states in themselves. So that's what we call by a finite state machine. How do we control it? It's very simple actually. There are 2 degrees of freedom only. One is that angle phi, which the body makes with the vertical. So we have to control phi to make this robot go forward, backward, or jump in one place. So we can use a very simple PD controller like K phi and B phi, which is a P and a D controller. And we can control that angle phi using a PD controller. Now we can control that angle L, that is the compression of the spring there. So 2 degrees of freedom. That also we can put a PD controller and take the difference in the position and the difference in the derivative of the position and put a PD controller there. So we have 2 degrees of freedom, which we are controlling using PD control, and we can make this this one-legged hopping robot go forward, backward, or hop in one place. Only it cannot stand. Now, going a little bit more forward, we said that we started off with one-legged robot. Okay, it has only one leg, but this one-legged fellow cannot stand in one place, so it's not of much use. Now, the moment you say you want it to stand in one place or carry load, then you have to increase the number of legs. So the next question that comes up is how do you increase the number of legs? How many legs? The moment you say number of legs, then what is the position of the legs? What is the orientation of the legs? Where is it fixed? So these are some examples of legged systems where we have a frontal position, sagittal position, mammals and reptiles. So mammals is the left bottom one where the legs are fitted right under the body. Okay, that is in the case of a horse or the case of a dog, the leg is like that. For a reptile, it's in the side. So when we're talking about legged system, we should also know how a leg is fitted and what is the kinematics of the leg. For example, shape of the leg. If you look at the top figure, the legs are straight coming below the body. Okay, that is for a human being, for example. Okay, now why are our legs like that? Essentially because if the leg were from the side, you can imagine that if the leg is directly under the body, like the one in figure A, then the total force, the weight of the body will be divided by 2, and it is going to pass through the leg straight onto the ground. Okay, so we spend a lot of time standing. So what will happen is the weight of our body will go through our legs onto the ground. There is no additional torque generated. Whereas if you look at figure B, what is happening because the leg is on the side of the body force will generate a torque just where the leg makes contact with the body. Okay, so because of in figure B, there will be an additional torque which is coming, which is not there in figure A. So this essentially shows the design of the legs and where the legs are fitted on the side or on the right exactly under the body. Now, figure A is mammals, it's human beings. Figure B is reptiles. Now, in the case of reptiles which are climbing walls, the body has to be maintained very close to the wall. Otherwise, the foot has to support a very high torque. Okay, so that is why the legs are on the side and the body is very close to the wall because these creatures climb vertical walls. The third one is that of an insect, for example, a cockroach. If you see the shape of the leg, it has a particular shape. Now, the shape of the leg is such for a cockroach in figure C, such that the torque at the body is very high because the torque arm, you can see the length of the leg is very high here. So the torque that will come will become very high. So cockroaches or insects need to change their direction or run very fast. Okay, because of which the leg shape is such that the leg shape and the leg design is such. So we saw that one-legged is okay for jumping in one place, but you need 2 or 4 legs to support weight or to have dynamic balance. And the way the leg is fitted, the number of legs all have a particular reason. Tails are sometimes used for balancing. Let's not worry about that. Now let's look at this. You might be familiar with this. You might be familiar with this video. One of the very famous videos of Big Dog, Boston Dynamics. Okay, it has 4 legs. Please pay attention to the shape of the legs. Okay, and the gait. By gait, I mean how many legs are on the ground, how many legs are in air when it is moving forward. You'll find that it is moving forward by using diagonal legs. So the diagonal legs are either in air or they're on the ground. And that is how it is maintaining balance. And it is very, very stable in the sense that even if you give an external disturbance, it can come back and get a restoring torque very, very easily. Okay. So this is an example of a 4-legged system, which is extremely stable and it has a particular gait. So one-legged is of not much use. Two-legged is okay for humans, but balancing is difficult. Four-legged is a little bit more stable, but then there is a question of gait on a four-legged system. Okay, so if you look at this, it can go in any kind of terrain, but please focus on the gait. It is moving on diagonal legs always. Okay, and if you look at the shape of the legs, they are bent backwards. Okay, let's move on. So what we saw is that we have to talk about gait of a system, and the gait essentially means the sequence of foot placement and balance. So what is balance? Very briefly talking about balance. If you look at the figure on the right, it has 6 legs. 3 of the legs are in air and 3 of the legs are on the ground. Now the 3 legs on the ground make a triangle. Okay, and the projection of the center of moment or the center of gravity has to lie inside that triangle when it is walking at all times. So this is what we mean by static balance. That a system is statically balanced if the projection of the center of gravity is always in the foot support polygon. And so it has to move in sequence of legs. So these 3 which are on the ground, okay, will ensure that it is balanced. In the next step, what will happen, all the 6 legs will come on the ground, and then the other 3 will go in air, and then they'll come on ground again. So the sequence in which they work, in which a legged system moves forward is all legs on ground, then some of them in air, some of them on ground, then again all on ground, then again reversing it that, some on ground, some on air. Okay, so if you look at two-legged, as we go along, we'll look at two-legged, and that is what we basically mean by a gait cycle. Okay, how we draw it? So it's drawn this way. The figure on the bottom shows the robot having 6 legs on the right, and the gait diagram on the left bottom shows 1, 3, 5, 4, 6 gait. So whenever the leg is on the ground, we mark it by a black line. So starting off at time is equal to 0, leg number 1, 5, and 4 are on the ground, 3, 2, and 6 are in air. Then at time, half the time, 3 by 6 is half the time, all the legs are on the ground. Then again, the other legs which were in air, now they are on the ground, and the ones on the ground are on the air. Okay, and it keeps repeating this. So this is what we call a gait cycle. This brings us to the first question of optimization. Is this the only way that it's possible to move the robot? The answer is no. You can have different gait diagrams. So the question comes up here is, which gait is going to give you the most energy efficient way forward? Okay, so this is where we require optimization, and also some amount of learning. We'll see where. So this is an example of a quadruped robot, okay, 4-legged. Watch the legs. 3 are on the ground, 1 goes in air, then 3 is on ground, again 1 goes on air. In that sequence, it moves forward, and that is basically what is called a gait. In this particular case, there are 3 on the ground always. Okay, then it becomes 4 on the ground, then 3 on the ground, 1 in air, and by alternately changing one leg which is in air, it can move forward. Okay, this kind of gait is called a creep gait or a wave gait. There are other ways by which it can move. In the case of the big dog, you saw that it was having diagonally legs in air, whereas in this case there is only one leg in air. Okay, so this is slower, that one is faster, but that is this is more dynamically balanced, and that one is less dynamically balanced. Anyway, let's move on. So if you're talking about kinematic modeling of this system, then essentially we are seeing that we have 4 legs, and whatever robotics you might have studied or mechanisms you would have studied, we can essentially put an axis frame on the body. My axis frame is 0, which is in the center, and then every axis has got an axis frame which is assigned to it. Okay, and then essentially what we need to figure out is this curve C. So the leg which is in air follows a curve C, which takes it from point A to point B, and you can have multiple curves. The curve C can be of different types. It can have different heights. If you are considering this to be a spline, then the spline can have different A, B points and different C points. So you actually have infinite solutions. Now this problem has infinite solutions because it has more degrees of freedom than required to move the body forward. Okay, so this is the first thing we are seeing, that this is a redundant system, and we have multiple solutions of this problem. Let's move further and look a little bit into what we call self-propelling machines. So this is the earliest people who studied dynamics and walking mechanisms, they first looked at a wheel. So on the left top side is the figure of a wheel, okay, on an inclined surface. Okay. Now, if this wheel is kept on an inclined surface, this wheel is going to start rotating and it will come down. Why does a wheel rotate? It rotates because if you see the projection of the center of gravity of the wheel is mg, and it comes down straight vertically, whereas the contact point that the wheel makes with the surface is slightly behind. Okay. So what happens is at the contact point between the ground and the wheel, there is a torque which is acting, or a moment, and this moment causes the wheel to go forward, to roll forward on an inclined ground. On a flat ground, the projection of the CG and that contact point will be the same, so it won't move. So if I make a robot in the form of a wheel and put it on an inclined ground, then it should be able to work by itself. Okay. So this is an example, the black stick figure. If you look at the two legs, they are designed like the spokes of a wheel. Okay, the two legs which are shown here having length L, they are designed like the two spokes of a wheel. And because it is designed like a wheel, if you put it on an inclined ground, it should roll forward. Okay, so that is so this is an example. Please have a look at this example. So this is what we call a passive walker. Okay, and it has two legs. It does not have any actuator. It can just walk down a slope. Okay, this is called what we call a passive walker, or a system or a machine which does not require any energy to walk. Where is it getting the energy from? It's getting it from gravitational energy. Because the legs are designed like wheels, it can simply keep moving forward. Okay, these are all examples of robots. This is another one. Okay, it can walk forward down a slope without any energy requirement because it is designed like a wheel, and it walks. These are called passive walkers, and they can keep walking. There are no motors you can see. It is just walking by itself. Okay. This is a toy. Okay, very interesting toy. In class, we normally ask the students to make this to study dynamics. So this, if you look at, it has two weights hanging on two sides, and it has two legs. The legs are designed like the rim of a wheel, and it moves from side to side and it goes forward. Again, no energy requirement. So these are what were called passive dynamics, and this is probably the simplest and the earliest working machines, where a system can walk by itself. After that, from passive, where no energy requirement is there, we have active systems where a lot of energy is required. Now, in these active systems, we have there are many of them, and we have very high degrees of freedom. For example, this has almost like 50 or 60 degrees of freedom, and they're actively controlled. The most advanced one is developed by Boston Dynamics called Atlas. Okay, so Atlas is able to walk by itself, open a door, go out, and it can walk in all kinds of terrain. Okay, now here this is probably the most advanced robot as of today, and it has vision cameras, it has lidars for mapping the terrain. It can compute the dynamics, and then it can walk on any kind of terrain and do any kind of task. Now the point here is because it has high degrees of freedom, maybe 60 degrees of freedom or more, you always have infinite solutions. So there has to be some kind of optimization that is required to find what is the best dynamic solution that is going to make this system walk from one point to another point. But the moment you talk of optimization, optimization takes time, so it cannot be done in real time. So it is not possible that this robot can do optimization in real time and then walk from one point to another point. Okay, it's not possible. Optimization normally takes minutes, if not hours. So if that is not there, then can we, if you want to operate the system in real time, then what can be done is that if we can learn the dynamics of the system, okay, in some way, maybe neural net or whatever way, support vector machine or whatever, such that it does not have to optimize the gate at each time, but using some kind of a lookup table, which it has learned already, it can actually find the gate. That is something we'll be looking at today. In terms of stability, if you look at stability of the system, so if you look at stability here, so this is about stability. Okay, so it falls down, it should be able to get up. Now, if you're doing online kind of optimization, it is not possible to find solutions in real time for this complex systems. Okay, then the other solution becomes maybe learning. Okay, it has learned. Now, it is also talking about the human aspect, that when we fall down, we get up, we walk. Is it that we are doing computation each time, or we are simply using learning? Because if you're doing computation, then the brain cannot compute at that speed. Okay, so it automatically shows that we are probably not doing optimization. We are doing something else, maybe like learning. So from here, let's move on a little bit to understanding. What is this optimization? What is this learning? How is it done? In terms of bipedal walking, I've just taken the example of bipedal walking. So in bipedal walking, that is human beings, the way we walk, our walk is classified into two planes mainly. One is the frontal plane. So this is my frontal plane, in which we are looking at, if you're looking at somebody from the front side, then the motion is in the frontal plane. And if you're looking at somebody from the side, then the body is on the side plane or the sagittal plane. You can of course look from the top and get a transverse plane also, but it's enough to look at the frontal and the sagittal plane. So in the frontal plane, the figure on the right, if you look at when you're walking, the person has to bend on one side. Okay, essentially we bend on one side, we bend on the leg on the ground to bring the center of pressure onto the leg on the ground. Okay, and then we take the left leg forward. So how do we walk? We essentially bend on one side, and then if you look at the left figure, which is on the side view, the leg on the left or at the back comes forward and the hip goes forward. So this is how we walk. We walk in two planes. So next time you walk, please look at yourself or look at somebody walking. What you'll see is that from the front side, the body bends on one side to bring the center of pressure onto the ground. And then from the side plane, the rear foot moves forward with a trajectory and the hip moves forward with a trajectory and the body goes forward. So this is essentially the way. So I'll just go back here. This is little, we need to understand this a little bit. So this is showing from the front plane. Okay, so the body moves from side to side. Okay, so this is an animation of a two-legged system walking in the frontal plane. Please note the body moves from side to side to bring the center of pressure onto the leg on the ground, and then it moves. Okay, otherwise balance cannot be maintained. This is essentially for balancing the system. Now, this is in the side plane. So if you're looking at the body from the side plane on the side, then it will look like this. So this from the side, the rear leg moves forward and the hip moves forward. Okay, so this is essentially how, let's look at this one again to understand how the system actually walks. And that black point is the center of pressure, which is on the ground. Okay, so by these two actions, the body moves forward and okay. So this we understand how the body moves forward. Now, from the side plane, if you see, the rear leg has a trajectory and then it comes forward. It follows a trajectory. So how many trajectories or which trajectory should it follow? They can be infinite trajectories. So the hip trajectory and the foot trajectory are infinite. It can take any infinite trajectories to move forward. That means we can all have different styles of walking and you're still walking. Okay, so there is a requirement for doing optimization to find which is the most energy optimal way of walking. Okay, so when we are walking, essentially we need to figure out the foot trajectory and the hip trajectory. So the foot trajectory is the one that takes the body forward, the foot trajectory and the hip trajectory. So there can be infinite trajectories. So each of us can walk in different ways, right? Because there are infinite solutions here. And how do we optimize that? Let's have a look. Now, if you're looking at balance, what is the meaning of balance? It basically means that if this is a bipedal system, then there is the leg on the ground, which is the point P, the leg P, which is on the ground. So it basically means that when you're standing on one foot, what would happen is the resultant torque and the moment about the point P, okay, should be zero. So if there is a resultant moment there, it is going to fall. That is the meaning of balance here. And that we can find very easily by using D'Alenber's principle. The So D'Alenber's principle says that each of these masses will be subjected to two forces. One force will be the gravity force, which is pulling it down. The other is the inertia force due to acceleration, which will be pulling it in the direction of the acceleration. So if we take the sum of the inertia forces and the acceleration forces, then that is going to be the force, the resultant force on the foot on the ground, and that will be balanced by the reaction from the ground, right? As per Newton's law, Newton's third law. So the forces from the top will be balanced with the forces on the ground, and they'll be balanced. Now, there is also a moment about here, and this moment is the one that causes the disbalance. So if the moment that there is about the ankle is zero, only then the system is balanced. And that we can find very easily by taking some of the moments also. So mg is xg cross mg is because of the moment caused by the gravity forces, and xg cross ma is the force is the moment caused by the acceleration force. Okay, so if you can make that equal to zero, then we say the system is balanced. And in bipedal walking, this point is called the zero moment point. We don't. It's called center of pressure, zero moment point. We don't say center of gravity. Center of gravity is more for a static system, whereas for a dynamic system, we don't say center of gravity. We say zero moment point because it's continuously changing. And something interesting here, if you look at the sole of your feet, of your own foot, okay, then when the person is walking, the zero moment point moves. Okay, if you think or you've ever analyzed how you walk, then essentially the zero moment point starts from the heel, it moves from the side, and then goes to the big toe, and then it goes to the other foot. So this is the foot on the ground. So the foot on the ground supports the center of pressure. The center of pressure starts from the heel of the foot, goes from the side, goes to the big toe, and then goes on to the other foot. So that is how we walk, human gait. Interesting thing is here is that the small fingers that you can see, okay, they don't support the center of pressure, so they have no requirement, and hence they are very small. And if you look at the arc of your foot on the top side, it also doesn't support the center of pressure, so it doesn't have any requirement. So our foot shape is such, or our foot shape has evolved or has been optimized in such a way that it is the shape corresponds to the motion of the center of pressure. This is something interesting that even we have evolved as per that. Now, let us look at the business of optimization here. So we have said that the robot moves forward, it can have infinite trajectories. Yeah, so how do we find which is the most energy efficient trajectory? So what we do is we assign frames, and after assigning frames, we find the relationship between the axis, one axis and the other axis, which is straightforward using the H parameter or simply by assigning frames. And then we do inverse kinematics to find the corresponding angles. Now this is very easy actually, not very difficult, because if you go back here, if I just go back to this figure, then we on the left side you see the stick diagram is going forward. There is a foot trajectory and there is a hip trajectory. Now this foot trajectory and the hip trajectory, if we divide it into 20 points or an equal number of points, then it is every point is connected by two links only. So if you look at the foot, which is the rear foot on the left side, then it is two link system which is connecting the hip trajectory and the foot trajectory. Now for two link systems, you know it's very easy to solve geometrically. Okay, so there are only two solutions. So for every point on the hip trajectory and the foot trajectory, there are only two links connecting it, and hence we know the solution geometrically, and hence inverse kinematics is very easy. It's not difficult here. So we can do inverse kinematics and find what are the corresponding joint angles when the body is going forward. Now, what are the variables? The variables are the foot trajectory and the hip trajectory can be all different trajectories. So we can use standard optimization techniques like gradient based, or we can use genetic algorithms to optimize the motion. What I mean is what GA will do, it will generate, so what it will do is essentially it is going to generate a very large number of foot trajectories and hip trajectories, and then find the corresponding energy required for it, and then say for which trajectory the energy requirement is minimum. Okay. Now, okay, so I move here now. So by doing that, we can find out what is the corresponding energy. Now we are optimizing what is the cost function. So we are trying to find what is the minimum energy requirement. Okay. So the minimum energy requirement, if you want to find the energy, then you have to find the torque, because torque into the velocity will give you the energy, into time will give you the energy required. And to find the torque at the joint, we can use dynamics, Newton-Euler or Lagrangian Euler, and find the corresponding torques at the joints. Okay, so this is Lagrangian Euler, and the equation comes out something like this. Okay, so for every joint, we can find out what is the torque. So if I just repeat again, what I mean by this is uh, our genetic algorithm, or in this case, we are using GA, is going to generate a large number of foot trajectory and hip trajectories. And for each of those foot and hip trajectories, it is going to find what is the corresponding torque required at the joints. And from the torque required, it is going to compute the energy. So integral of the torque into d theta, theta dot, which is the velocity, this is differential theta dot into dt will give us the total energy required. Okay. So when it is taking one step forward, we can find the torques, and from the torques, we can also compute what is the energy required for the system to go forward. So what G is essentially doing, or the optimization is essentially doing, is it is using infinite number of trajectories, and for each of them, it is finding the energy, and then saying for this trajectory set of trajectories, it is giving us the minimum energy. And if you do that, what we do find is, so this is using GA, and what we can find is this is an energy optimal trajectory. So the stick figure on the right gives us the energy optimal trajectory of the foot and the hip. Okay, so the curve looks like an S curve. So the rear foot goes up, then it comes down, and then remains parallel to the ground, and then comes to a stop. Okay. Now the interesting part here is we said that all human beings in our legs, we have 16 degrees of freedom. So each leg has 8 degrees of freedom. So it is 3 degrees of freedom at the hip, 3 at the ankle, 2 at the knee. And so two legs have 8 plus 8, 16 degrees of freedom, which means that you have infinite solutions actually for inverse kinematics. So theoretically, when all human beings walk, we should walk differently. Right, this is something to note or to understand from here, that in a redundant system like bipedal walking, there would be infinite solutions. So all human beings should walk differently. But if you look at when human beings walk, we walk more or less in the same way. Okay, and that is interesting, and it shows that we follow this kind of a trajectory, an S kind of a trajectory. All of us do that, and this is proof from dynamics and what we just talked about from optimization, that this S kind of a trajectory is the minimum energy trajectory, which means that human beings are optimized for minimum energy walk. So either we have learned it or we have evolved that way, that whenever we walk in a trajectory which takes minimum energy. So when we do a task, we also take minimum energy. And we are either evolving that way, or we have, I don't know whether we have been optimized that way. Okay. But something to note, that human walk is optimal in terms of energy. Now, so this is how we do optimization and the need for optimization. This is a redundant system. You have infinite solutions. You have to find the energy optimal way of doing it, and this is how we find it. So this graph shows an energy optimal way of avoiding an obstacle. Okay, so this is the optimal trajectory for going over an obstacle. This is for climbing stairs, and this is very much the way human beings also walk. Again, proving that human trajectories are energy optimal. There are a couple of new issues in bipedal locomotion. Very briefly, we can go through them. For example, walk with soft sole. So if you look at the sole of our foot or of our shoes, it is soft. And because it is soft, there's going to be some deformation there. Okay, so we can model this deformation by using things like FEM, or by making simple models, spring mass damper models, or spring models only, actually it's called the KX models, to look at the deflection of the sole of the foot. Now, in the human sole, we have soft tissue. Now, what is the function of this tissue again? If you look, essentially the function of this tissue is to absorb shock when we are walking, and also to reduce energy when we are walking. So this is something that was proved, that if you change, so this is a model that was built by us long time ago, that if you change the material properties of the sole of the foot, what we find is that The response when it is walking, if it is very soft, it will start vibrating a lot. If it is less soft, it will oscillate a little bit. But if it is just optimal, the system is not going to oscillate. So this actually proves that there is also a reason for having a soft sole, and one of the reasons is to save energy when we are walking. Let us move forward. If we are moving forward of bipedal walk, then what we look at is, if you're looking at our legs, and we see that in our legs, the structure of our legs, we have muscles, and these muscles are connected by tendons, and the tendon is connected to the joint. Okay, so this is the basic structure of the human leg, and and this shows that the actuator is the muscle, and there is a tendon there, and the tendon actually behaves like a spring, like a passive spring, and this spring has spring-like behavior. So what we thought about is, a lot of people have done this, is by putting some amount of compliance in the joint of robots and seeing what happens. Okay, so this is a robot where we have an actuator, then there is a torsion spring, and the torsion spring is connected to the motor, and then the other end is connected to the joint. And if you put a torsion spring, then the dynamic equation actually changes like this. So this is D, C, and so this is inertia. Uh, D, H is the Coriolis centrifugal, C is gravity. So because of the spring, this KT, the spring constant will come in, and our dynamic equation becomes like this. Okay, and again, if we do optimization and try and find the optimal energy of walk of a system which has springs at the joint. So this is a robot which has spring at the joint, something like this. So this one has a tendon. In this one, there is a spring. Okay, and if you try and optimize it again to find the optimal trajectories, then what we find is that the optimal trajectories look like this for different values of spring constants. So the left, middle, and the right figure are for different K values. K is the spring stiffness. So this is showing that for different spring stiffnesses, the optimal walk is going to be different, the optimal trajectories. This graph is interesting in the sense that for different values of K, the energy requirement is different. And if you look at the graph, there is stiffness of 0.5 for which the energy requirement is minimum. So this essentially means that the energy requirement is minimum for a particular stiffness, and which means that we cannot use any stiffness. The stiffness has to be optimized. Okay? So this is an example of a system with compliance, or a robot with a compliant joint, which has a spring, and the spring stiffness value is optimized, or you get minimum energy for a particular stiffness constant. Now, if you look at look further into this example, this is an interesting example again in terms of design, in terms of control, in terms of optimization. That if you add springs to the system, you tend to save energy, you tend to make it safe. But then we know that when we are walking, we are on single leg stance, then a double leg stance, and the leg is once on the ground and once it's on air. So which means that the stiffness I was talking about, okay, cannot be a constant stiffness, so it has to be a variable stiffness. And in the human leg, our stiffnesses are variable stiffnesses. So biological systems can change their stiffness depending on whether we are on single leg stance, double leg stance, or leg in air. Whereas for a mechanical system, the moment I put a spring, a mechanical spring, the stiffness gets fixed. You can't change it now. So this is one big challenge of robotics design today, or design of mechanical systems today, where we need to design systems where we can change the stiffness. And it's a challenge because few examples have been made. People have tried to make examples of variable stiffness actuation, but we are still not able to make actuation or vary actuation the way biological systems can change their stiffness. So this is a challenge in terms of having stiffness is good, but it's a challenge of how to make it, how to control it. These are some other examples of adding compliance. Why am I going into compliance? Because in terms of research, there is a lot of talk of making systems which are safe. Okay? How do you make it safe? You can make it safe by making it soft. You can make it soft by making the joints soft. That means I put compliance in the joints. So that is how safe robots, or robots which are working with humans, called human
robot interaction, robots for human robot interaction, these robots. And if you put compliant joints again, then we can do FEM to find the deflection of the joints, and based on those deflection of the joints, what we can do is we can find what is the optimal gating. Something interesting here is that if you look at the top right figure, so this is the zero moment point which is moving from leg to leg. This is the top view. So this is the top view, and these are 2 feet. Okay. So if you look at it, the zero moment point appears to be vibrating a lot when it is moving from one leg to the other leg. Okay. That is because we have put compliance in the link, and that link is causing vibration. So if you look at this video here, so this is a robot which has, so let me just explain this one. So what we have basically done is this is a rigid link robot, biped robot. This is the left side one is the front view. The right side one is the left side view, is the side view. So all the links are rigid. Okay. So we have taken off the knee joint, and in the knee joint we have put a compliant link there. So this is the rigid link. This is a compliant link. So this is the knee joint. The knee joint to the ankle joint, we have put a compliant link, which is a semicircular link. This is how we have made the rigid link system into a compliant link system. And this is the example of the compliant link system. So you can see that just below the knee joint there is a C-section, and that below is compliant. So when the robot walks, you can see that there is a lot of vibration which comes in. So we have made it compliant. It is good for jumping. It is very good for running because it can take energy and give back the energy. But in the process, there is a lot of vibrations which has come inside because of this compliance. So something quite interesting also is that in the human legs there is no vibration because we can actively switch the compliance or the stiffness. We can change it as we are moving. But this robot, because it has a mechanical compliance, it cannot shift the compliance, and that is causing the vibration. So theoretically, we should be having a compliance system in which we should be able to actively vary the compliance or the stiffness of the system. Okay. Now that is still a challenge. We have not got that far, but these are some examples of mechanical designs, control optimization using stiffness. Now let's move further and look at. Now we have a biped robot. Now we want the robot not only to walk on the ground inside the lab, but we want it to go outside and walk on terrain, on three-dimensional terrain, or terrain containing obstacles and ditches. Okay. Now, so far we have been talking about optimization, and I explained how optimization is done to get minimum energy. Now we see that if you want to do that kind of optimization for one step, just one step, it takes about 2 to 3 hours. So obviously in real time it can be done. Now, if you cannot do it in real time, then what is the other thing that we can do? The other way to think about this problem is when human beings are walking, are we doing dynamics? Are we doing optimization in our head and then walking? Probably no. Not probably no, it's not, it's a no. Why? Because then we'll never be walking. To do one step, we'll be computing for 3 hours and then we'll do one step. So we are doing something else called learning. Now, what is this learning mean? So one way is for every step, if I go back to the optimization we were talking about. So if I just go back here to the optimization we talked about here and said that, so this is where I started off from by talking about optimization and said the hip trajectory and the foot trajectory can be infinite, right? Now, but that is only for a given step length. So if you look at the step length, what I mean is the length of the step that it moves in one step, the rear foot moves from here to there, that is one step. Now that's a variable actually, right? Also, this example is for a flat ground. If we are going on, on an inclined ground or a three-dimensional terrain, then there is going to be an inclination also. Okay, so the footstep length is going to vary, and the terrain inclination is going to vary. Okay, so apart from the hip trajectory and the foot trajectory being variables, being infinite, you can actually have infinite inclinations of the ground, and you can have infinite step length also. Okay, so in total, this is an infinite into infinite problem. Okay, that means for every step length, if you're going to learn, then you have to learn it for infinite step lengths and for infinite inclinations of the ground. Okay, because real time can be done. So if the robot has to walk on three-dimensional terrain, one way is this is the 14 degree of freedom robot. So one way is we take this, we discretize the step length and we discretize the terrain. And for each of those discrete events, we can learn offline what is the optimal trajectories. Okay, and once we have learned that, we make a big database and we learn that database. So for this robot, what we have done is it has 14 degrees of freedom, and the step length is a variable. So the step length from here to here is a variable, and the hip trajectory is a variable. So these are two variables. So it can have different step lengths. So there is one variable. So we discretize that into say 50, 60, 70, 80, 90, 100, like that. And each of this, for each of this, we find what is the optimal trajectory. That is on flat ground. Now, on an inclined ground, again, we discretize the inclined ground, say 5-degree inclination upward or downward. And for that 5 degree, the step length is again discretized. Okay. Now it can turn. So for a right turn of 5 degrees, again it is discretized. Okay. So for a turning radius of 5, 10, 15, 20, and for going up an incline again 5, 10, 15, going down an incline 5, 10, 15, each of this is going to have multiple. Is going to have multiple uh, optimal solutions, optimization solutions. So what we do is for each of these combinations, we get a number of optimal parameters, which is the inclination upward, inclination downward, angle of turn right, angle of turn left, and the step length. So these are all variables. We discretize it into 555 millimeter steps, and then for each of this, we find what is the optimal trajectory. Okay? And that becomes so we basically we do the dynamics, what I just explained. We find the energy optimal trajectories, and then what we do is we find the this is how it is done for an upward inclined ground. So when the robot is going upward, the vector, the normal vector, which is on the which is going to be on the foot, can lie anywhere in this cone, which is the friction cone. Okay. So basically, we optimize this, and then for each of this, we find what is the corresponding. Yeah. Okay. So now this is an example of the data set which is created. Now to create this data set, I said that there are a lot of variables. Right turn angle, left turn angle, going up, going down, and step length. So for each of this, if it takes 2 hours for one optimization, and you have about 30,000, then it is 3 hours into 30,000. That much time it will take to make this data set. But once this data set is generated, what we can do is we can learn it now. Okay? Now, so once we learn it, then we can operate in real time. So this is also an example of optimization and learning both together. Okay, so we optimize each of these step trajectories and then we learn. And after generating this data set, what we do is we learn it using a neural net. We can learn it using anything else. Okay, so this was basically a feed-forward neural network that was used, and with one layer in between, and one of the hidden layers, the hidden layer is having 90 neurons, which is and the input and the output is trained, and then we basically learn this data set. Which means that if the robot has to turn right by 5 degrees, it knows what is the optimal trajectory it has to take. Now, if it has to turn by 2.5, it can extrapolate between 0 and 5, and then find the corresponding trajectory. And that can be done real time. So this robot now has learned its ways of walking, and it can go on three-dimensional terrain and take its corresponding. So this is an example of optimization, need for optimization, and need for learning, where it's not possible to do something in real time or it's just impossible. Okay, but we have learned it, and once you have learned it, then it works. Now, this is an example of a robot going up an incline. It is having different gradients actually. Okay, so the different shades of color are different gradients. So it is going from the green line to the red line, and finding its path and finding its footstep, and it is walking in real time because it has learned. This is another example of robot avoiding an obstacle, and there are also ditches on the ground, so it can also avoid. It can walk over the ditch, okay, in real time because it has learned how to walk. So this is what we mean by learning how to walk. Human beings also probably we learn, and because we have learned to walk in particular terrains, we can walk in real time. We don't do dynamical optimization in our heads. Okay? Now, this only talks about one footstep. What about a path? You want to go from one point to another point in space. You must have a path. You must generate a path. So there are two terms which are used. One is path planning. The other is motion planning. Okay. Now here, if you're going from one point to another point, uh, let me come here. So if you're going from one point to another point, uh, from here I'm going there, you can go in infinite ways. These would be the paths by which it can go, which is basically called path planning. How to find the path to take you from one point to another point without hitting an obstacle, without getting into a ditch. But when you're following the path, you have to give joint angle commands at the joints, okay? Which means control will be at the joint level now to take the system from here to there to follow the path. That is what we call by motion planning. Okay, so these two terms, which are sometimes used interchangeably, but they're not the same. One is path planning, just to find a path to go from one point to another point without hitting an obstacle. The other is how to follow the path exactly. Okay, and that is what is called motion planning. Motion planning is at the joint level. Now, so how do we do the path planning for this kind of a robot which can go on three-dimensional terrain? So what we can do is we can use, there are many algorithms. Maybe when I talk tomorrow, I will talk about some algorithms of path planning and motion planning. So one algorithm which we use here is the what we call the wavefront propagation using ethanol function. So the wavefront propagation is like the way the waves move, okay, on the surface of a lake or a pond. If you drop a stone, then the wave will be generated and the wave is going to move. Now, if you look at the extreme right side bottom figure, the green and the blue, so the wave is going to move depending on the gradients now. So wherever there is a high gradient, the wave will move less in that direction and it will move more in the direction which there is a lesser gradient. That is the whole idea of wavefront propagation. And we can basically use this wavefront propagation to go from one point to another point and find a path. So in path planning, basically what we are doing is we are going from one point to another point. So this is an example of a three-dimensional terrain. So it has inclinations and the robot has to go from one point to another point. It is basically using a wavefront generator to generate a wave to go from one point to another point. The wave is going to take the least gradient or the least resistance path. So automatically it's becoming energy efficient. So this is one example of generating a path. Once you have generated the path, you have to walk on the path. That is motion planning. So to walk on the path, we have already learned the data set of walk. So by the example I showed some time back, so the neural net has already learned how to walk in 3D terrain. So now, once I find the path, I can walk on the path using the neural network. So I can use the wave propagation wave generator for generating a path, and then I can walk on the path using the learning network. So this can be used on any kind of terrain. This is an example of a terrain with an obstacle. The one on the left is showing the obstacle. The one on the right top is showing the potential value, basically. It's showing the gradient values. So the path with the red line, which is going from one point to another point, avoiding the high gradient. And then we can work on it based on the learned neural net. Now, if I put obstacles like ditches, so this one is giving you a ditch. The one on the figure on the left is showing a three-dimensional terrain with a ditch of all kinds of shapes. So the path planner has to find the path that will take it from one point to another point and across the ditch. Okay? And the motion planner is going to find out the footsteps that it is going to follow the path to take it from one point to another. The figure on the right top is showing the values of the gradients. Basically, the internal function is the gradient map. So the high gradients are the ones which are shown by high value. So the path is going to avoid this high value and find the path which is going in the low value and then follow the path. This is an example of crossing a ditch. So the robot is standing at the far red corner. It has to cross the ditch, find the path which will take from here to here. Then it has to walk on the path. So you can see that it has found the path which can take it across the ditch, and then it has to walk on the path. Now it is doing that almost in real time because it has already learned how to walk. And this is three-dimensional terrain, so it is 3D. Now 3D means that at every grid, the normal can have three angles with the three axes. So that's the meaning of 3D. So this is an example of where we have done optimization. We have done learning of that optimization. And then we can use motion planning to find the path from one point to another point. And then we can follow the path using motion planning, the path planning and the motion planning. So these are examples of going from one point to another point by using optimization and learning. So Biped is one example where we have to use some kind of learning. We have to use some kind of optimization. So I think that is all for today. I started a little late, but I think we are on time now. So if there are any questions, I can answer. Otherwise, we will stop here. So if there are any questions, you can send it to me.
Hello.
Hello.
Yes, sir. Sir, I am Neeraj from Nagpur,
Yeah.
assistant professor, and I have done my PhD thesis in robotics.
Okay.
So it was mobile robot, not biped robot.
Okay.
So my question is that when we do the motion planning of both the legs,
Yeah.
left and right leg,
Mhm.
how do we take care of the center of gravity so that it is balanced by one leg at a time?
Okay. Yeah. So that I had explained some time back that if you look at what do we mean by balance, so this I had explained here. I went a little bit fast today, and it's a little bit difficult to explain on slides. That is the other problem, but I'll just go through it again. So, what do we mean by balance? So, it basically means that if you're looking at this figure, the leg which is marked P is on the ground, and there is one leg which is in air. Okay, that means when we walk, uh, our gait is two leg, one leg, alternately like that. So when we are on one leg stance, then this leg on the center that you can see on the left side is on the ground, and the rear leg moves forward, which is in air. Okay. So the leg which is on ground is subjected to two kinds of, it's subjected to forces and is subjected to moments. Okay. So the each of the mass, the lump mass of the links will be subjected to a gravity force and to an acceleration force. Each of the masses, so Mi, M1, M2, M3, M4 are all subjected to gravity forces and acceleration forces. And the total force that is going to come on the foot on the ground will be the sum of the forces experienced by all the masses due to gravity and acceleration. So that's the top equation. So the total force is equal to mg minus ma, which is the total force which is acting on the leg on the ground. Now, the leg on the ground, the force which is acting on the leg on the ground will be pointing downward, okay, because it is supporting the weight. Now, this force which is pointing downward will be balanced by the force which is the reaction force from the ground, as per Newton's third law. Okay, so this forces which is acting downward and the ground reaction force which is acting upward will balance each other and to be cancelled. So this is always balanced in terms of forces. But there is also a moment. Now this, because one leg is in air and one leg is in ground, each of these masses, there is a force which is acting downward. So there is going to be this force into the distance from this point P. That will be a moment. So this, there is also going to be moments due to mg and because of ma. Now this moments are the fellows which have to be balanced. If the moments are not balanced, then the system is going to fall. So this balance is taken care of by the zero moment point. And how this is computed is, if you look at this leg on the ground, okay, if I can talk about the leg on the ground, then this has a force which is acting on it, which is this one, which is this one. Let's call it Fgi. Now this force into a distance wherever this force is acting. Okay, so that force into the distance to the ankle will be a moment. Plus there is a moment mg which is created because of this. So if this moment and this moment are balanced, okay, then we say that the system is balanced. And how do you compute it? We compute it by this equation, the last one, Pz is equal to the moment, okay, divided by the forces. So this will give you a point P about which the zero moment point is active. So it is a little difficult to explain in terms of slides without writing.
But if you go to this Wikipedia and just search for zero moment points, zero moment point in Wikipedia is explained very nicely. It's explained this way only, and you can have a look at that. It becomes very clear then how balance is enforced. Okay. Are there any more questions?
Good morning, sir.
Yeah. Hello.
Hello. Good
Yeah.
morning, sir.
Yeah. Good morning.
Sir, I want to know how we can just if I want to make a robot, then how it will be programmed. Then which programming language will be preferable to make it?
Hello.
Hello.
Yeah. So the simplest robot you're talking about
Ji,
serial arm, I guess, right?
ji sir, ji sir. Actually, I am new in this field.
Yeah.
Means to this workshop, I go.
Yeah. So the easiest way to control nowadays, you have the servo motors. Servo motors are already pre-programmed. Okay, they have a PID controller inside with a potentiometer, and they are calibrated to move from 0 degrees to 180 degrees. And you can control them using PWM of a microcontroller. For example, Arduino or Atmega 1632. That is the easiest.
Okay, sir.
Okay, so there are no more questions, so we can stop now, I think.
Sir, there are few questions in the chat box, sir. Kindly you can see.
Where is the chat box?
Sir, you can access their chat in the middle of the new screen, sir. On the main page of the meeting, sir, where you have shared the screen.
Okay, yeah, okay, I got it. So there are some chats.
Yes, sir.
Okay, so here there is, is there a difference between path planning and trajectory optimization for UAVs? So, so path planning is essentially finding a path from one point to another point, and motion planning is at the joint level where you're actually controlling the actuator to follow that path. Okay, so here the question is path planning and trajectory optimization. So trajectory means trajectory is the time history of position, velocity, acceleration, which is at the joint level. Okay, so this is motion planning. So it is path planning and motion planning basically for UAVs. So we can find a path to go from one point to another point for a UAV, but when the UAV is flying on that path, you have to control the actuators of the UAV, and that would come under trajectory optimization of the UAV. Okay, which can be called trajectory optimization or motion planning of the UAV. So that is controlling the actual actuators of the UAV. So the question on programming languages I have just answered. So there is the simplest robot is servo motor made, and then you can use Arduino or Atmega 16 to control it because it is already pre-calibrated. So serial arm can be made very easily using that. Then there is a question: is legs walking speed fixed because human body